In this video, we'll be assessing a CTSF deletion variant for eligibility towards ASO therapies. To begin, we first conduct a variant check and see whether an ASO is already available. We can use tools such as Variant Validator, which is described in greater detail in the SCN1A example. For this example, the variant is correct and no ASO exists. Next, we check for inheritance pattern. As suggested by our guidelines, we can use OMIM to conduct this check. We see here that the phenotype associated with this gene is a result of autosomal recessive inheritance. Next, we check the pathomechanism. If we look up this variant in ClinVar, we can see here that this variant results in a premature termination codon predicted to cause truncation or absence of the protein due to nonsense-mediated decay in a gene where loss of function is a known mechanism of disease. Since the variant is a deletion leading to frameshift and termination, and there is no evidence of its effects on splicing, we can go straight to step 4. We know the variant is loss of function and autosomal recessive, so our only option is to assess for exon skipping. To keep it simple, we assess for factors that call for quick exclusion when evaluating for eligibility towards canonical exon skipping ASOs, including checking whether the variant is in the first or last coding exon, whether it is out of frame, and whether a stop codon is formed. Using the UCSC genome browser, we input the gene name and location, which is highlighted here. We can then see the specific nucleotide that's affected. By mousing over the exon on our transcript of interest, we see here that this variant is an exon 2 of 13. We can also see here that the exon consists of 99 base pairs coding for 33 amino acids. By plugging the transcript into ExonViz and checking off Show Non-Coding and Show Exon Number, we can see here that the exon is not the first or last coding exon, it is in frame, and the codons on either end are coded entirely by the second exon, and there is no possibility of forming a stop codon if we were to skip this exon. Additionally, we can use Ensembl, which shows here that our exon consists of 99 base pairs and has a start and end phase of 0. Therefore, our exon is in frame. Next, we want to check the size of the exon that is being skipped. In our guidelines, we note that a loss of greater than 10% of the protein product may result in loss of function, as per ClinGen recommendations, so we want to see whether skipping the exon could result in losing greater than 10% of the coding transcript. To get the total size of the coding sequence, one can use the RefSeq database and just input the transcript of interest. Scrolling down to the feature section, we could see which part of the transcript is actually protein coding. Here we see that base pairs 121 to 1575 are protein coding, which totals to 1455 base pairs. If we remember from our earlier analysis, exon 2 consists of 99 base pairs, which accounts for around 6.8% of the coding transcript. We can also check the size of the exon being skipped by looking at the number of amino acids the exon codes for and dividing it by the total protein length. Using the UniProt database, we see here that the protein consists of 484 amino acids. If we remember from earlier, our exon codes for 33 amino acids. This, once again, equates to 6.8% of the total protein length. So we know that the exon is the second coding exon, it is in frame, no stop codon will be formed if we join the adjacent exon, and that the exon is less than 10% of the coding transcript. We now want to see if the exon codes for an important protein domain. I'll be showing you one approach for doing this assessment. There are many ways of doing this part, and oftentimes this may be the longest part of the analysis. It's important that one employs multiple strategies in this assessment, as highlighted in the guidelines. One approach for this analysis is to search the UniProt database. This is a good starting point because it consists of multiple publications and databases that can provide detailed information on the protein itself. So here in the search bar, I input the gene name and a few results are generated. I will click on the entry for the human protein. When you click on the protein, you are taken to the entry page. There are multiple pages that you can navigate. The page I'm showing you here is the Gene Coordinates tab. We can see here that this second row corresponds to the second exon, and that these are the G dot coordinates. And here we have the corresponding P dot coordinates. So exon 2 codes for amino acids 72 to 104. This is important to know because we want to evaluate important domains in amino acids that fall between this range. It is important to just verify these coordinates as well. You could do this by plugging these coordinates into the UCSC genome browser and seeing if they correspond to the exon of interest. In this case, they do. If we go to the Feature Viewer tab, it gives us an overview of important domains, sites, transcriptional modifications, among other annotations on this protein. The numbers up here are corresponding to the amino acid position. As stated, we are interested in amino acids 72 to 104. If we zoom into that range, we can see here that there are no important domains, sites, or structural features coded for by these amino acids. This would be indicated by a colored bar. However, we do see here that this region plays a role in molecular processing. If we click on the drop-down menu next to molecular processing, we can see here that this range codes for a propeptide, which is removed in the processing of the mature protein. However, given the fact that there is no important sites or domains that may be involved in this processing step, we can probably skip this exon. Again, there are many strategies on assessing whether an exon codes for a domain, so we also encourage you to read through the Entry tab, as well as to browse through the Publications tab to learn more about the protein in greater detail than what is shown on the Feature Viewer. So now that we know that this exon is in frame, does not result in losing more than 10% of the coding sequence, does not create a stop codon, and there are no functional domains coded for by this exon, we can classify it as likely eligible.